I'm Pascal Maillot and the Deputy Head of Unit of Quantum Technologies and HPC in the European Commission. So thanks for inviting me to these Q2B sessions. Today I'd like to tell you about the quantum technologies perspective in the EU in the view of the European Commissions and the flagship that the European Union develops in quantum for the next years. First, I'd like to say that quantum is not new. Quantum technologies is not new in the European Union and the European Commission. We have begun the project in quantum technology in 1999 under a program called FP5 at that time. And until 2018, the European Union has spent around 500 million euros on the research on quantum technologies. So over 20 years. At the beginning, the main objectives were more research to develop the quantum technologies and the first commercial products. But now we switch clearly to the quantum flagship, which is clearly based on applications and not only research to put on the market quantum-based devices, either in communications or computers, sensors, for a market that we estimate will be huge in the coming years and will bring many progress in the European Union and worldwide. So, as I was mentioning, the flagship began in 2018. The quantum flagship is the 1 billion euro over 10 years, and the ramp-up phase has just finished some months ago, and we are going in 2020 in the full implementation of this quantum flagship. Here you have a picture of all the activities we are doing in the quantum technologies in the European Union. So you can see that there is a part of research which began under Horizon 2020 program and will go on with Horizon Europe. These is mainly the quantum flagship with its main pillars, the computers, sensors, communication, and simulators. But besides that, we have Quantera, which makes the links between the different member states and ensure the coherence between the different national programs. This is for the research part, but we don't limit ourselves only to the research part. As I said, the goal is to have applications, real and concrete applications of these quantum technologies. And we plan to develop under the Digital Europe program a quantum communication infrastructure in Europe named EuroQCI, which 25 member states having signed the declaration for this. We have planned also to deploy a quantum communication and simulator infrastructure, and also an infrastructure based on sensors. So as I mentioned, the quantum flagship is based on a strategic research agenda designed by a group of strategic experts. And we have the four common pillars that we often see when we talk about quantum technologies: communication, computation, simulation, and sensors. There is basic science working across all these, as we are far to understand everything in the quantum science. So we still need investment in basic science to go further in the comprehension of these technologies and these theories. Across also, we have a part for education training, software to support the applications of the quantum computer, and engineering. I would like here to make an aparté on the quantum computer, which is clearly more the specificity of this seminar. So in quantum computing, it's a whole ecosystem that we want to develop. It's not only focusing on the hardware, but also the quantum software and the optimization process to control this quantum hardware. We have also hybrid projects to have high performance computer linked with quantum accelerators. And the ultimate goal will be the quantum internet, where these quantum computers will be interlinked via quantum communication, via the quantum communication infrastructure. And that's why you can see in the slides mentioned the quantum network and secure communications. In quantum computing, until during the ramp-up phase, we have developed two prototypes of quantum computer, one based on the trapped ion technologies with a demonstrator of 10 qubits and a prototype of 50 qubits. The project is called Action. We also have another project called Open Super Q, working with superconducting qubit technologies and achieving a fidelity of higher than 99% with a 7 qubit machines. These are the two projects that we funded. Now, as I said, basic science is still a domain important for us to fund, and we have Square, the quantum computer. The project is called Square, which deals with rare earth ions, and Micro QC, which is based on microwave driven quantum logic on the chip. And I would like to point out that this micro QC could give birth to a spin-off Universal Quantum, which has raised almost $5 million US to operationalize the platform. On the applications of the flagship, so I talked about ion trapped and superconducting qubit, but recently we also began a project called QLSI based on semiconductor technologies, where again, we would like to address systems that are over 1,000 qubits, and linked with that, as I said before, we go for an ecosystem, not just the hardware. So we have also a project called NIASK for algorithm research and design, whose goal will be to have a software dealing with practical applications of the quantum computers. I would like to give you here some figures at the midterm after 18 months of these projects. More than 1,400 scientists are involved in this project, going and participating to several conferences and workshops. 236 organizations involved, 1/3 of them being private, more than 20 startups, and several spin-off. From these projects, we have 60 patent applications, whose 16 are already granted, and a huge amount of publications in the most prestigious reviews coming from these different projects. So it's really a contribution of all the projects in the European Union to provide all these very impressive figures, and it shows also a great collaboration between the different projects of the flagship. These are still rather based on the research. I would like to give you a hint now about the infrastructures I was mentioning at the beginning of my presentation. We don't focus only on research, but also on infrastructure. On infrastructure, I would like to give the example of the Euro QCI, so the Euro Quantum Communication Infrastructure, which is based on cybersecurity concerns with the advent of the quantum computer, which will be able to decrypt our our communications. So the QCI will be based on QKD devices, and it's a pan-European project interlinking the different member states. The declaration of support for the establishment of this QCI in Europe was signed by 25 member states, and we plan to deliver trusted communication based on quantum key distribution, being an infrastructure upgradable until later the future quantum internet in the next decades, I would say. The main principle of the architecture is a ground segment interlinking the different national QCI with a complement by space, a constellation of different satellites who will do the communications for the distance over 80 kilometers, for example, or for the communications overseas. For the budgetary period, here on this slide, it's still under negotiation, but you can see that Horizon Europe is providing 1 billion euros for the technology supply and fundamental research. These technology supply, when ready, will feed the Digital Europe program, where we will develop for the moment the super computing infrastructure, high performance computers. We have the quantum computing hybrid infrastructure, a mix between HPC and quantum accelerator, and also the quantum communication infrastructure that I've just mentioned. Connecting Europe facilities, CEF2, will be used for the interlink between the different national QCI that we call cross-border link. And up to 8 billion euros for Euro HPC. This is for the supercomputing infrastructure and the quantum accelerator. Here, you can have an overview of the roadmap. So the HPC, we are now in the pre-exascale technologies, and from 2023, 2024, we will go towards the exascale one. The quantum computing will progress in parallel with this high-performance computer. Not only on the hardware part, but also on the software part to create a complete ecosystem. And in parallel also, we have the development of the quantum simulation towards more than 1,000 quantum units until 2021. From 2022 until 2027, we expect to have prototypes that will outperform the HPC, and that will perform tasks that the current supercomputer won't be able to do. For the quantum computer, we are now at around 50 qubit for tolerant roots, and for the coming years, we expect to go until 200 qubits and more in the future. One of the main parts is to increase the error correction of these qubits to reach the highest high fidelity qubits for the correct functioning of this quantum computer. Here it is. Thank you to all for listening, and that's the end of my presentation.